I'd like to welcome everyone to this last tutorial of Monday, and I think we're in for a wonderful treatment. Let me tell you a little bit about Daniel Kuhn. He has an interesting background. He has a master's degree in theoretical physics and a PhD in economics, and he's currently the chair of risk analytics and optimization at EPFL in Lausanne, Switzerland. His group has been working on providing the necessary theoretical background to justify the use of machine learning, in particular data-driven optimization. So in a robust context, and I think that you'll get a lot out of this theoretical but a treatment that sort of puts on a good firm theoretical basis things that people are doing and should be doing in terms of sampling and using machine learning. So without much further ado, it's a pleasure to introduce Daniel Kuhn.
Thank you very much, Douglas, for the kind introduction, and I would like to thank the organizers first very much for inviting me to give this tutorial. And also thank you all of you for being here so late in the evening. So my tutorial is based on joint work with Peyman Moituri and Esfahani from TU Delft, and with my fantastic PhD students, Viatan Nguyen, who is somewhere in the audience, I suspect, and Sarouche Javiezadeh Abadeh. So in this tutorial, I would like to study decision problems under uncertainty. And we're going to assume here that each decision results in an uncertain loss function, L of xi. Here, the random vector xi captures all the uncertain parameters that affect our decision problem. And I'm going to assume that this random vector follows a distribution P. So the set of admissible decisions is denoted by script L here, capital script L. So in this setting, I'm going to define the loss, the risk of a loss function L as the expected loss under with respect to the distribution P. And I'm going to refer to the optimal risk as the infimum of the risk over all admissible loss functions. So you think of this as a sort of an abstract way of formulating one-stage stochastic programs where I don't explicitly introduce a notation for decisions. I just do that to avoid clutter. It will make the formulas less heavy later on. So these one-stage stochastic programs have many applications. They're routinely used in news vendor problems, in portfolio selection problems, but also in regression and classification problems in machine learning. And we'll see some of these examples later on. So unfortunately, the distribution P that we need to evaluate the risk of a particular loss function is hardly ever given to us in applications. Instead, we most of the time only have limited structural and statistical information. So in the remainder of the talk, I'm going to assume that we know a set capital Xi that is known to contain the support of our unknown distribution P. And moreover, I'm going to assume that we have access to n independent samples from this unknown distribution. So like in machine learning, I'm going to refer to these samples as the training samples. So in this situation, we could just simply replace the unknown true distribution with a nominal distribution p hat that is estimated from the data. As this distribution p hat is constructed from observable quantities, it is accessible, and therefore the resulting nominal risk evaluation problem and the nominal optimal or a decision problem are at least theoretically solvable. So I'm going to use mostly throughout the talk the following non-parametric and parametric models for the nominal distribution. So in the absence of any structural information, it's quite natural to set the nominal distribution to the empirical distribution. This is just the uniform distribution on the training samples. It's a discrete distribution. In the presence of structural information, it's often convenient to model the nominal distribution as an elliptical distribution with a given density generator G. So once this density generator G is fixed, the elliptical distribution only depends on the mean vector mu hat and the covariance matrix sigma hat. So these are the only parameters that then need to be estimated from the data, and this could conveniently be done with maximum likelihood estimation, for example. Now, as it is constructed from limited noisy data, the nominal distribution is invariably subject to estimation errors. Unfortunately, estimation errors in the inputs of an optimization model have a detrimental effect on the optimization results. And this is just a manifestation of the notorious garbage in, garbage out phenomenon. So I would like to demonstrate this phenomenon with a simple example. Let's assume that we're given 10 different projects with different net present values, visualized by the blue bars on this slide. Let's assume that we have enough money to fund 5 out of these 10 projects. And I would like to address the question, which 5 projects should we implement? The answer seemed quite simple. It seems that we should just implement the 5 projects that have the highest net present values. And in doing so, we will maximize the average net present value across the chosen projects, which is visualized by the red dashed line here. Now, unfortunately, net present values, they're never quite exactly known. And in practice, they would have to be estimated by using statistics or by using expert opinion. So they're invariably affected by estimation errors. Now, for the sake of argument, let's assume for a moment that half of these projects have been net present values have been overestimated, and the other half projects have net present values that have been underestimated, so that the estimation errors cancel out on average. This is actually not such an unreasonable assumption if there are many projects. Now, a decision maker who doesn't see the true net present values, but only the noisy estimates, will rank these projects differently, namely as follows. And such a decision maker who solves a nominal decision problem will then decide to fund the 5 projects that have the highest estimated net present values. And now you see the problem. The problem is that projects whose net present values have been overestimated are much more likely to be selected than those whose net present values have been underestimated. So the estimation errors do no longer cancel out across the chosen projects, but they're actually positive on average. So that means that the decision maker is too optimistic about what can be obtained. In fact, of course, the true average net present value across the chosen projects is lower than the maximum that could have been achieved under perfect distributional information. So this means that the decision maker is too optimistic. So the red line basically here on the slide represents what the decision maker believes to earn, whereas the blue line represents what the decision maker will actually earn. So you can think of the red line as what is obtained in sample in the optimization problem, and the blue line is what is obtained out of sample. The difference is positive, and it's sometimes referred to as the out of or the post-decision disappointment. So in summary, we see that even if the input estimates of a decision problem, of an optimization problem, are unbiased, the optimization results are biased. And actually, they're biased in the wrong way and lead to disappointment once we implement the decisions. Now let's return back to our abstract setting, where we have this nominal distribution we had estimated from the data, which is affected by estimation errors due to the noisiness of the samples. So a natural question here would be, can we quantify this phenomenon? Actually, so I should have said that this phenomenon is frequently called the optimizer's curse. So in decision analysis, people refer to this sometimes as the optimizer's curse. This is reminiscent of overfitting effects in statistics. So in the general problem, can we somehow quantify this optimizer's curse? In order to answer that question, we need to agree how we're going to measure estimation errors in the nominal distribution, in the input. To do so, we need a distance measure between distributions. And it turned out that a good distance measure that has many nice properties is the Wasserstein distance. So the Wasserstein distance has been studied by many famous people, some of them shown on this slide. And it is very convenient for us to assess the magnitude of this optimizer's curse. So I'm going to work with Wasserstein distances of different types P, where P is a number greater than or equal to 1. So the type P Wasserstein distance between two distributions Q and Q prime is defined as the Pth square root of the optimal value of some transportation problem. Now, if Q and Q prime are distributions on Rn, then this transportation problem optimizes over all couplings of Q and Q prime. So a coupling is a distribution on R2n whose marginals are equal to Q and Q prime. Intuitively, the optimal value of this transportation problem can be interpreted as the minimum amount of money that we need to pay to transform one pile of dirt, represented by the first distribution Q, to some other pile of dirt, represented by the second distribution Q prime, if the price we need to pay for transporting a unit mass from origin from point psi to psi prime is just given by the distance between psi and psi prime to the power p. So actually, the transportation problem is just an infinite dimensional linear program over all couplings. And it actually admits a strong dual linear program. Actually, before I talk about that, so actually, if any distribution Q prime that has a finite Wasserstein distribution, finite Wasserstein distance to a given distribution Q, can be obtained by reshaping this distribution Q at a finite transportation budget. So that means we can move potentially a small probability mass a long distance, or we can move a large mass a short distance, but we may not be able to move a large mass over a long distance. So transportation cost is mass transported times the distance that is moved. Okay, so the transportation problem admits a strong dual linear. The transportation problem admits a strong linear dual linear program, and that results in an alternative characterization of the Wasserstein distance. So in fact, the dual linear program can be interpreted as the profit maximization problem of a third party that moves the dirt distribution Q to Q prime on behalf of the problem owner by buying dirt at the origin xi at a price phi of xi, and then sells dirt at the destination location xi prime at the price psi of xi. So the price functions phi and psi here are the decision variables of this third party. The constraints ensure that the problem owner prefers to use the services of the third party for any origin-destination pair xi and xi prime, instead of moving the dirt independently on her own at her own transportation cost. So a particularly important Wasserstein distance is the type 1 Wasserstein distance, where P is equal to 1. If P is equal to 1, then one can show that at optimality, the prices for buying dirt and for selling dirt will be equal at each location. So in this case, that means that the type 1 Wasserstein distance between Q and Q prime can be expressed as the difference between the profit of selling the dirt distribution Q prime minus the cost of buying the dirt distribution Q, maximized over all price functions phi that are Lipschitz continuous with Lipschitz modulus 1. So this is actually the celebrated Kantorovich-Rubinstein theorem. Okay, so I promised you that if we measure estimation errors in the input distribution by using the Wasserstein distance, then this gives us a way of estimating or quantifying the optimizer's curse in our decision problem. So to see this, let's assume that our loss function is Lipschitz continuous with Lipschitz modulus L, with Lipschitz constant L. Let's also assume that we found an estimator for which we know that its type 1 Wasserstein distance to the unknown true distribution is smaller or equal to epsilon. So epsilon is an upper bound on our estimation error. In this case, we could ask the question, we know that the estimation error in the input is smaller or equal to epsilon. How big is the optimizer's curve? So how big is the estimation error in the risk of that loss? Now, it turns out that because if we divide our loss function by the Lipschitz constant L, then the resulting function has Lipschitz modulus 1 and can be interpreted as one of the pricing functions in the dual transportation problem. So the Kantorovich-Rubinstein theorem, therefore, allows us to conclude that the estimation error in the risk, so the difference between the nominal risk and the true risk, is bounded above by the Lipschitz constant of the loss function times the epsilon, the estimation error in the input. Similarly, if we look now at the decision problem, where each decision corresponds to a different loss function, and if you assume that all these loss functions are Lipschitz continuous with the same Lipschitz constant capital L, then one can again prove that the estimation error in the risk is bounded above by L times epsilon. So this analysis shows us, or gives us a rough understanding of how estimation errors in the input are propagated to the result of the optimization problem. In fact, estimation errors in the input are simply amplified by the Lipschitz constant of the loss function. So this reasoning suggests that if we would like to mitigate the optimizer's curves, if you would like to have a small estimation error in the risk, then we should try to find an estimator that has a small Wasserstein distance to the unknown true distribution. Unfortunately, if we have a finite number of samples, then all estimators are subject to fundamental performance limitations and cannot be improved beyond a certain point. For example, the type 1 Wasserstein distance between the unknown true distribution and its closest discrete distribution with n atoms is bounded below by 1 over the sample size to the mth root of the sample size, where m is the dimension of the uncertainty. So that means no discrete distribution can approximate the unknown true distribution better than this expression here, which decays very, very slowly, actually, with the sample size. So no estimator can do better if we want to restrict ourselves to discrete estimators with n discretization points. Now, interestingly, the empirical distribution, which just places mass 1 over n on each of the randomly selected training samples, essentially attains this bound in a probabilistic sense. So in some sense, the empirical distribution is the best estimator among all discrete estimators that we could pick. Similarly, if for some reason we knew that the true distribution was an elliptical distribution with a known density generator, then we would only have to estimate the mean vector and the covariance matrix. These would be the only parameters that are to be estimated. Now, we know from the Rao inequality that any unbiased estimator for these parameters has a covariance matrix or the covariance matrix of any such unbiased estimator multiplied by the square root of the sample size must exceed the inverse Fisher information matrix. So again, there is a fundamental limit to the extent to which you can improve the estimator. So this actually also means that maximum likelihood estimators are essentially optimal. Okay, so the optimizer's curve seems to be fundamental. And if you have finitely many samples, it cannot be avoided. We can try to improve our estimator, but that will only be possible to a certain extent. Interestingly, however, once the potential to improve the estimator has been exhausted, we can actually further reduce the optimizer's curves by changing the decision problem, the optimization problem that we're solving. So that's the interesting observation. There are actually several ways how you could do that, but the way that I would like to suggest to you in this talk is that I would like to robustify the nominal decision problem against all distributions under which our nominal estimated distribution has an estimation error that is small. So specifically, what I'm suggesting is to construct an ambiguity set in the space of distributions. This ambiguity set is constructed as the set of all distributions supported on that set capital Xi that we know to contain the support of the unknown true distribution, and for which all distributions have a type P Wasserstein distance that is smaller or equal to epsilon from our nominal distribution. So in some sense, you can think of this Wasserstein Ball as the set of all distributions under which our estimator has an estimation error of at most epsilon. And the radius epsilon of this ball could be interpreted as the maximum estimation error against which you seek protection. So in this case, we can then use this Wasserstein Ball to robustify our risk evaluation and decision problems. So specifically, we can define the worst case risk as a supremum of the nominal risk over all distributions in the Wasserstein Ball. And we can define the worst case optimal risk as the infimum of the worst case risk over all admissible loss functions. So this worst case optimal risk problem is our decision problem. And this is actually a distributionally robust optimization problem because it represents a game where the decision maker first picks a decision, that is a loss function, and then some fictitious adversary, people usually think of it as nature, chooses a distribution in the ambiguity set to inflict maximum damage. So now you might raise the question of why this is a good approach to model decision problems under uncertainty. And I tried to compile a list of my favorite reasons for why I like this approach, and you may agree or disagree with those, but let me just go through the list quickly. So first of all, I think that these distributionally robust models are just more honest than the nominal decision problems. And because by specifying the radius of the Wasserstein Ball, we give the optimization problem some information about the degree of the estimation errors. In contrast, the nominal decision problem pretends that the nominal distribution is completely exact. So we're just more honest. Second reason might be that from the optimizers curves we've seen that if you solve a nominal decision problem, then in sample, you're too optimistic. Out of sample, you're disappointed because you can't meet the promise. So nominal problems, they overpromise and they underdeliver. In contrast, distributionally robust problems, they underpromise because we adopt a worst case approach. And unless the worst case distribution materializes, then we'll do better out of sample. So these problems overdeliver. So in some sense, these problems are just better at managing expectations. Third reason, that's an important one, it turns out that many interesting distributionally robust optimization problems with Wasserstein balls can be reformulated as tractable convex programs, and we will see that later on. The fourth reason is also important. So by using a Wasserstein ball, we can leverage many interesting results from probability theory, measure concentration results, and so on to develop new generalization bounds and out-of-sample performance guarantees for the solutions of these models. So if we apply the distributionally robust approach to classification and regression problems in machine learning, then it actually turns out that we can, in some cases, recover classical regularization methods that have been used successfully in statistics. So this means that if successfully used techniques from statistics can be recovered as special cases of this approach, then maybe this approach isn't so bad. But in contrast, it gives us new probabilistic interpretations of maybe some more heuristic techniques that have been used. Number 6. So if you solve a nominal decision problem with the empirical distribution, the discrete empirical distribution, then you basically pretend that you cannot see samples in the future that you have not already seen in the past. By using a distributionally robust approach, where you allow some fictitious adversary to move these samples around anywhere in space at paying some transportation cost, we're actually anticipating some low probability, potentially high impact scenarios that could be important for our decision. So you could refer to these as black swans. Seventh, it's also possible to come up with some very intuitive axioms that will guarantee that any rational decision maker faced with a decision problem under ambiguous distributions will have to solve a distribution robust optimization problem. And number 8, that's a bit more complicated to explain. So abstractly speaking, when we solve a decision problem, a data-driven decision problem, what we try to do is we take some data and we try to transform this data to a decision that will perform well in the future. Turns out that if you look at this problem very abstractly, then you can prove that an approach that has an optimal trade-off in terms of what the method will promise that you can achieve and what you can actually achieve out of sample is that you should solve a distribution robust optimization problem. OK, so we'll see some of these things more clearly later on. So far, this was just my introduction, a very long introduction and motivation. Let me right now dive deeper into the topic. So in the first part of the talk, I would like to argue that you should actually expect these distribution robust optimization problems to be very hard to solve. One reason for that is that Wasserstein balls contain many discrete and continuous distributions, even if the nominal distribution is discrete. Here's an example. Assume that psi is a univariate random variable without support constraints. Let's assume that the nominal distribution is the empirical distribution on 3 training samples. Let's also assume that we would like to consider a Wasserstein type 1 ball of radius epsilon equals 0.7. So this Wasserstein ball contains many continuous distributions. For example, it contains this uniform distribution between A and B. It also contains many mixtures of normal distributions centered at the training samples, as shown in this video here. But besides all these continuous distributions, the Wasserstein ball contains also many discrete distributions that can be obtained by moving the training samples around or splitting them up and so on. It is even possible to move some training samples infinitely far away, provided that we reduce their probabilities appropriately. For example, it is possible to move the 3rd training sample here to the right by any amount theta. As long as theta is smaller than n times epsilon, the whole sample can be moved. But beyond that point, so that we don't exhaust our transportation budget epsilon, the probability that is moved needs to decay as epsilon over the displacement. The remaining probability mass has to stay at the original location of the training sample. It's also instructive to visualize a type 2 Wasserstein ball. Similar story applies. It contains many continuous and many discrete distributions, and it's again possible to move probabilities, to move training samples to infinity. In this case, however, if we move the 3rd training sample infinitely far to the right, then its probability needs to decay quadratically with the displacement theta, because in the type 2 Wasserstein distance, the transportation cost grows quadratically with the displacement. It's also instructive to visualize the extreme case of a type infinity Wasserstein ball. Actually, in this case, we can freely move the training samples around or reshape them within a ball of radius epsilon around the location of the corresponding sample. So the type infinity Wasserstein ball is actually the only one in which it is not possible to move probability mass infinitely far away. And in some sense, this is the only Wasserstein ball which does not protect you against these black swans I mentioned before. There may be some scenarios that are too far away from all your training samples. So all of these suggests that Wasserstein balls are extremely rich. And in fact, it turns out that it's extremely difficult to determine whether a given distribution is inside a Wasserstein ball or not. More formally, we can prove that it is sharply hard to compute, to determine the Wasserstein distance between 2 distributions Q and Q prime, even in the very simple setting where Q is the uniform distribution on the unit hypercube in d dimensions, and Q prime is a discrete distribution with only 2 atoms. So I'd like to sketch the proof. And to do so, I'd have to recall the definition of a knapsack polytope. So a knapsack polytope is just the intersection of the unit hypercube in d dimensions with an arbitrary half space. Now, as any half space that contains 0 can be expressed as the set of all points that are closer to 0 than to some other point w, we can actually encode the knapsack polytope by this point w and denote that by p of w. So Dyer and Fries have shown that computing the volume of the knapsack polytope is a sharply hard problem. Now, let's denote by q the uniform distribution on the hypercube, and by q prime the two-point distribution that assigns probability mass alpha to 0 and probability 1 minus alpha to w. If you would like to calculate the Wasserstein distance between these two distributions, we have to find the optimal transportation plan. And that assigns, OK. Now, this video shows or visualizes the optimal transportation plan. It shows in turquoise all those scenarios of the uniform distributions that are assigned, that are moved to 0. And in magenta, all the scenarios of the uniform distributions that are moved to w under the optimal transportation plan. On the right-hand side, you see how the distance between the two distributions changes as the probability alpha of the point 0 changes. You can also see that this distance is minimized exactly if all scenarios that are actually closer to 0 than to w are transported to 0. In this case, the amount of mass that is transported to 0 is exactly equal to the volume of the knapsack polytope. And that means if we were actually able to efficiently compute Wasserstein distances between uniform distributions and discrete distributions, we could also efficiently minimize that function here. And we could thereby efficiently compute the volume of a knapsack polytope. But this contradicts the hardness result by Dyer and Fries. So I've argued that we should expect these Wasserstein distributional bus problems to be hard to solve. So maybe a more modest goal would first be to find bounds. So I would like to suggest 3 simple bounds on the worst case risk of a given loss function. The first bound is an optimistic lower bound, which is obtained by restricting the Wasserstein Ball to only discrete distributions, which are actually obtained by perturbing the samples of the empirical distribution. So actually, I should have said, we work here with the empirical distribution. That applies only to that case. So in that case, to evaluate the worst case risk over this restricted Wasserstein Ball, we need to solve this optimization problem over the parameters theta I, which are just the displacements of our training samples. This maximization problem is probably easy to solve if the loss function is concave in the uncertainties. So in this case, this lower bound would be easy to compute. We can also come up with a pessimistic upper bound. Indeed, one can show that the worst case risk is always bounded above by the Lipschitz regularized nominal risk. So it's always bounded above by the nominal risk, so the actual risk under the nominal distribution, plus epsilon times the Lipschitz modulus of our loss function. In fact, it's very easy to prove that this upper bound holds by just using Jensen's inequality and the Kantorovich-Rubinstein theorem, but let me not go into details here. So we have this upper bound. Now there is a third upper bound that only applies if p is equal to 2. So that only applies for the type 2 Wasserstein distance, which is a very important special case. For the type 2 Wasserstein distance between two distributions q and q prime, we can prove that the distance admits an analytical lower bound in terms only of the mean vectors and the covariance matrices of these two distributions. So of course, this lower bound can always be easily computed, even if the exact Wasserstein distance between the two distributions is very hard to compute. This lower bound was first discovered by Gelbrich in 1990, and I'm going to denote it by dg from now on. So this Gelbrich bound actually can be interpreted as a distance measure on the space of mean covariance pairs. So this is a distance measure or a metric on that space. Very interesting observation is that this Gelbrich lower bound is actually exact if Q and Q prime are two elliptical distributions with the same generator. So for example, if they're both normal distributions. So in order to derive a conservative upper bound on the worst case risk over a type 2 Wasserstein Ball, using this Gelbrich bound, I first need to introduce an uncertainty set U epsilon in the space of mean covariance pairs. So this uncertainty set, in fact, is just defined as a ball in the space of mean covariance pairs with respect to this Gelbrich distance, which is centered at the mean vector and the covariance matrix of our nominal distribution, which are here denoted by mu hat and sigma hat. So if we denote by T the mapping that transforms any distribution Q to its mean value and its covariance matrix, then Gelbrich's theorem from the previous slide implies that any distribution in the type 2 Wasserstein Ball is mapped by this mapping into the uncertainty set U epsilon. So the image of the Wasserstein Ball under this mapping is a subset of U epsilon. And as the Gelbrich bound is exact for elliptical distributions, one can actually prove that this mapping is surjective when the nominal distribution is elliptical. So we can now use this uncertainty set to define another ambiguity set in the space of distributions. So we can define the so-called Gelbrich hull as the pre-image of our mean covariance uncertainty set U epsilon under this mean covariance projection T. So this means that by construction, the Gelbrich hull is an ambiguity set that encapsulates the type 2 Wasserstein Ball. Moreover, if this Gelbrich hull contains some distribution Q, then it must contain also any other distribution with the same mean vector and covariance matrix. So therefore, the Gelbrich hull could actually be much, much bigger than the Wasserstein Ball in principle. However, because this is an outer approximation of the Wasserstein Ball, we can bound the worst case risk of a loss function L by the Gelbrich risk, which we defined as the worst case expected loss now over all distributions in the Gelbrich Ball. So in the rest of the talk, I'm going to refer to this as the Gelbrich risk, and I'm going to denote it by this R with a bar and subscript epsilon. OK, so we've seen three bounds that are maybe or maybe not easy to compute. What I'd like to show to you in the third part of the talk is that actually all of these bounds are tight. They're exact in interesting situations. And in these situations, they can also be computed efficiently. So the key tool to develop tractable reformulations for worst-case risk evaluation and decision problems is a strong duality result, which expresses the worst-case risk over a Wasserstein Ball equivalently as the optimal value of a convex minimization problem over a scalar variable gamma. In fact, this gamma is just a dual variable of the Wasserstein constraint. So this strong duality result was first developed for p equals 1 and for discrete nominal distributions on finite dimensional spaces, but was later dramatically extended to arbitrary p and to arbitrary nominal distributions, even on Polish spaces. So this convex minimization problem involves actually the Moreau envelope of our loss function. The Moreau envelope could be viewed just as the negative informal convolution of the loss function L, whose worst case risk we want to compute, and the transportation cost. So as an example, if the loss function is given by this negative absolute value of xi, then and if p equals to 2, so the transportation cost grows quadratically with the distance, then the Moreau envelope just looks like this negative Huber loss function. So this strong duality result can be used for example, to derive tractable reformulations for worst-case expectations of piecewise concave loss functions. So a piecewise concave loss function is just a pointwise maximum of finitely many concave component functions Lj. Okay, so this leads us to a first main theorem. So let's assume for the moment that our set xi is convex and that the nominal distribution is the discrete empirical distribution on the training samples. Let's also assume that the loss function is piecewise concave. In this case, we can prove that the worst case risk equals the optimal value of a finite convex minimization problem. First of all, this problem involves a constant q, which is just related to the p through the usual pq conjugacy relation. And it involves a constant phi of q, which is defined as this ratio here. So first, this is indeed a convex optimization problem. In particular, the third constraint group involves the convex conjugate of the negative component functions. It involves the support function of the convex set xi, and it involves the perspective function of the dual norm to the power q. So all of these are convex functions. So in fact, this problem scales only linearly in the number of samples and in the number of components, of concave components. So therefore, under reasonable conditions, this problem can be solved very efficiently. In fact, this is a new result. So previously, such a reformulation was only available for the type 1 Wasserstein distance, for p equals 1. However, with my fantastic postdoc Trevor Chen and Wolfram Wiesmann, we managed to extend this result to arbitrary p. So since this is a minimization problem, it can also conveniently be combined with the minimization over the decisions in the outer decision problem. So we can reformulate our overall decision problem as a simple single minimization problem that we can attack with standard solvers, for example. However, this convex minimization problem also admits a strong dual maximization problem, which can be interpreted as a finite reduction of the worst case risk evaluation problem. In fact, this dual maximization problem looks a bit like the problem of maximizing the expected value of the loss function over a set of discrete distributions that are obtained by perturbing the training samples. This analogy is precise in the case when we only have one component function Lj, so when the overall loss function is actually concave. In this case, actually, this problem coincides exactly with our robust lower bound that I presented to you before. So the robust lower bound is exact, it's tight, if the loss function is concave in the uncertainty. And it can be computed efficiently if the loss function is convex, because then this is a convex problem. So one can also prove that this dual problem is always solvable. So let's just denote the optimal decision variables by alpha star ij and theta star ij. Now it turns out that these optimal decision variables can be used to construct an extremal distribution that attains the worst case risk, if such a distribution exists, or can be used to construct a sequence of distributions that converge to the worst case risk if no single distribution attains this worst case risk. So in fact, this extremal distribution is discrete, and it's obtained by applying a simple transformation to the discrete empirical distribution. Specifically, if the optimal variable alpha star ij is strictly positive for some I and j, then what we should do is we should move a mass alpha star ij over n from the ith training sample by an amount theta star ij divided by alpha star ij. So we should move this sample a bit in the direction of theta, or part of that sample, of the probability mass. On the other hand, if the alpha star ij is 0 for some I and j, then one can prove that the corresponding theta star ij is an element of the recession cone of the set xi. So this means that the set xi extends to infinity along this direction. And in this case, what we should do is we should move a linearly decaying mass infinitely far in the direction of along this recession direction. So this will create a sequence of distributions that will asymptotically attain the worst case. So let me summarize. If the loss function is piecewise concave, if the nominal distribution is a discrete empirical distribution, and the set xi is convex, then the worst case risk can be computed by convex optimization for any p between 0 and infinity. And this generalizes earlier results, which were only available for p equals 1. In fact, if the loss function L is concave and the nominal distribution is empirical distribution, then we just recover the robust lower bound from before, which is therefore exact. The dual maximization problem can be interpreted as a finite reduction of the original infinite-dimensional worst-case risk evaluation problem. This problem is always solvable, and its solution can be used to construct a worst-case distribution, which actually may not exist in the case where p equals 1. But in that case, it can be used to construct a sequence of distributions that are asymptotically worst case. Interestingly, one can prove that if p is bigger than 1, a worst case distribution will always exist. OK. Now let's look at a different setting where the loss function is convex. And let's assume now that the set xi is the whole space, so no support constraints. In this case, we can prove that the worst case risk with respect to the type 1 Wasserstein distance exactly equals the Lipschitz regularized nominal risk. So it's equal to the nominal risk plus epsilon times the Lipschitz modulus of the loss function. So this looks like a simple reformulation of the worst case risk evaluation problem. But in fact, it is actually intractable. The reason is that it is NP hard to compute the Lipschitz modulus of a convex function, even if that convex function is second-order conic representable. However, we will see interesting examples where we don't need to solve an optimization problem to find the Lipschitz modulus, so where this is basically available analytically to us. So to give you some more insights into this result, let's look at an example. Let's assume again that xi is a univariate random variable without support constraints, and that the nominal distribution is the empirical distribution on 3 training samples. Let's again look at the type 1 Wasserstein Ball of radius 0.7. Let's also assume that the loss function is convex and piecewise linear, like as shown here. And let's now try to solve the worst case risk evaluation problem. So what we have to do is we have to reshape our discrete empirical distribution in a way such that the expected value of the loss becomes as large as possible. Turns out that what we have to do to achieve this is to move the third training sample infinitely far to the right by any amount theta, and thereby we need to decrease its probability by 1 over theta. So the video here shows in the upper panel the perturbed nominal distribution under which we calculate the expected value, and the lower panel shows how the expected value of the loss function changes with the displacement theta. So you can see that asymptotically, this expectation converges to our upper bound. So this proves 1, that the upper bound is tight, and 2, that the distributions we constructed on top, moving the third training sample infinitely far to the right in the direction of steepest descent of the loss function, that this sequence of distributions is asymptotically optimal, or worst case. Let's look at another example where the loss function is quadratic. So to maximize the expected loss function over all distributions in the Wasserstein Ball, we still need to move the third training sample infinitely far to the right, which is the direction of steepest descent. In this case, however, the expected value under these perturbed loss functions diverges. It will grow indefinitely to infinity. And this is, of course, no contradiction, because the Lipschitz modulus of a quadratic function is actually infinite. So in this case, the upper bound is actually meaningless. So main takeaway points from this are, if the loss function is convex, and we have no support constraints, and if p equals to 1, then the worst case risk coincides with the Lipschitz regularized nominal risk. So this upper bound is tight in that case. One can prove that actually no distribution will ever attain the worst case risk in that case, except if the loss function is linear. Otherwise, we always have to construct a sequence of distributions where we send one of decaying probability mass infinitely far in the direction of steepest descent of the loss function. You should bear in mind that computing the worst case risk is generally hard because we need to compute the Lipschitz modulus of our convex function L, which is NP hard in general, but which we can do in interesting applications actually, as we will see later. So let's now turn to the third bound, the Gelbrich bound for the type 2 Wasserstein distance. So recall that we upper bounded the worst case risk over type 2 Wasserstein Ball by the Gelbrich risk, which was obtained by inflating the Wasserstein Ball to the Gelbrich hull. Recall also that our mean covariance projection maps any distribution in the Wasserstein Ball to an element in the mean covariance uncertainty set U epsilon, and that the Gelbrich hull was defined as the pre-image of this uncertainty set U epsilon. Now let's assume for a moment that we denote by P, mu, and sigma yet another ambiguity set. Actually, I call this a Chebyshev ambiguity set because it contains all distributions that have a given fixed mean value, mean vector mu, and covariance matrix sigma. These are the quantities that are available in the Chebyshev inequality. So we can actually therefore express the Gelbrich hull as the union of all Chebyshev ambiguity sets over all mu and sigma in our uncertainty set U epsilon. So remember that the Gelbrich risk was defined as the worst case expectation of the loss over all distributions in the Gelbrich hull. And because of our decomposition of the Gelbrich hull into a union of Chebyshev ambiguity sets, we can write the Gelbrich risk as a nested optimization problem where the inner problem evaluates the Chebyshev risk, so the worst case expectation of the Chebyshev ambiguity set, and the outer maximum maximizes over all mean covariance pairs in our uncertainty set U epsilon. Now the inner problem here is just an infinite dimensional linear program over all distributions subject to finitely many moment constraints. So we know from global sensitivity analysis that the maximum of a linear program is concave in the right-hand side coefficients, which are the vector mu and the matrix sigma plus mu mu transpose, which is the second-order moment matrix. However, as the second-order moment matrix depends in an indefinite quadratic way on the mean vector, the overall optimal value of this problem is actually non-concave in mu, and therefore the outer problem over the convex uncertainty set U epsilon appears to be hard. However, we can reparameterize the inner linear program in terms of the second-order moment matrix, denoted by n. Then the optimal value of this problem becomes concave both in mu and m. At the same time, we can also reparameterize the uncertainty set U epsilon outside in terms of mu and m. This is achieved by just transforming the uncertainty set U epsilon under this indefinite quadratic transformation f. Now, usually, convexity of a set is not preserved under quadratic functions, but this particular uncertainty set has a lot of good structure, and it turns out that actually the image of U epsilon under f is another convex set. So this means that the outer problem is actually a convex maximization problem. And this should give you some intuition for why it is easy to solve the Gelbrich risk problem for any loss function. So in some sense, this generalizes earlier results in distribution robust optimization, where people have tried to come up with ways of robustifying the Chebyshev risk against moment uncertainty, and there were only very partial results with somewhat contrived uncertainty sets for these moments, and this only worked for special loss functions. So this is quite general. So this can be applied, for example, to calculate the Gelbrich risk of a piecewise quadratic loss function, which consists of finitely many the pointwise maximum of finitely many convex, concave, or indefinite quadratic functions. So assume that we have no support constraints and the loss function is piecewise quadratic. Then we can actually use these techniques to show that the Gelbrich risk equals the optimal value of this finite convex program convex minimization problem, or its dual maximization problem. As before, the primal problem can be used to reformulate the decision problem, so we can be merged with the outer minimization over the decision variables. And the maximization problem can be used to gain insights about the worst-case distribution. So this maximization problem, again, is always solvable. So let's just designate all optimal variables by stars. And one can now prove that the distribution that attains the Gelbrich risk, Q star, can be represented as a mixture. So each quadratic component function, Lj, contributes one mixture component, Q star j. And the mixture weights are the optimal decision variables alpha star j from the dual maximization problem. This distribution, Qj star, has the following properties. It's supported on the set where the jth component function exceeds all the other component functions. And it has first and second moments that are determined by the solution of the dual maximization problem. So we know that the worst-case distribution has this structure. Interestingly, however, and we can compute this solution efficiently, but we cannot construct efficiently these components Q star j. This is a hard problem. So in summary, the Gelbrich bound bounds the Wasserstein risk, and if the Wasserstein risk provides an upper confidence bound on the auto-sample performance, then so does the Gelbrich risk. So it inherits its statistical guarantees. The Gelbrich risk can be computed by convex optimization. It induces this uncertainty set U epsilon from mu and sigma, which leads to an outer robust program that is convex for any loss function and generalizes second layer robustness results from the earlier literature. So one can prove that the Gelbrich risk coincides with the Wasserstein risk, so it is exact if L is a quadratic function and the nominal distribution is elliptical. So that means the third bound, the Gelbrich bound, is also tight in this setting. The worst-case distribution is available in sort of closed form if L is quadratic and the nominal distribution is elliptical, but it is hard to compute in a more general case where L is piecewise quadratic. So now we have some applications in machine learning, but it turns out that time runs out. OK. So this is the last part, I promise you. So we can apply these techniques to classification problems where we would like to predict a binary output from a continuous input. So let's denote by xi the combination of the input x and the output y. Let's assume it follows a distribution p. You can think of the problem of where you have a bunch of digital images that show cats and dogs. And so the input is, you can think of it as a high-dimensional vector of RGB values. And the output is a label that is equal to +1 if the image shows a cat and -1 if it shows a dog. So the ideal predictor would be the one that predicts a cat if the probability that the output is +1, conditional on the image, exceeds 50%. Of course, that ideal prediction is not available because the distribution P is not known. Instead, we are only given training samples from the unknown distribution. And in this case, it's customary to look for linear predictors, which predict the label or the output as the sign of W times X, where W is some weight vector. So the prediction is correct if W times X has the same sign as Y, or if Y times W transpose X is positive. So we can measure the prediction error by a loss function that is small if the prediction is correct, so if this product is positive, and that is high if the prediction is wrong, so if this product here is negative. So popular examples include the hinge loss from support vector machines, the smooth hinge loss that irons out the kink at 1, or the log loss, which is used in logistic regression. So a naive approach would be to solve an empirical risk minimization or expected loss minimization problem. So this problem just uses the empirical distribution on the training samples to minimize the prediction loss. This is the nominal decision problem. What we propose here is instead to robustify this problem by using this Wasserstein distribution robust approach over a type 1 Wasserstein Ball. So what we in order to define the Wasserstein distance on the space of input-output pairs, we need to specify a norm on that space that determines our transportation cost, the cost of moving around probability mass, right? And what I'm going to assume here is that this distance measure is additively separable with respect to inputs and outputs. There's one parameter kappa here, which quantifies the relative importance of the outputs. So in some sense, you can think of kappa as the cost that you need to pay if you want to flip a label from +1 to -1. So we can prove the following theorem. If this kappa parameter is equal to infinity, and p is 1, then the worst case prediction loss is equal to the Lipschitz regularized nominal loss. In this case, the Lipschitz constant of our loss functions can be computed. It's actually the Lipschitz constant of the univariate loss function capital L times the dual norm of W. So you recognize that if kappa is infinity, which sort of means that there is no label uncertainty in our problem, flipping the labels is infinitely costly, so we assume the labels are correct, then we recover a classical regularization method, which has been used always in statistics, right? We have a norm term. Now we see that this needs to be the dual norm of the norm that we used on the feature space to measure transportation distances on the input space, right? And the weight of the regularization term is just the radius of the Wasserstein Ball, the estimation error in the input, times the Lipschitz modulus of the loss function, which is actually 1 for all the examples I've shown you. We can also make similar arguments in case of regression, where we try to predict a continuous output from our input. And we have the same setup. We have an unknown distribution P that determines the input-output pairs. So in this case, the ideal predictor, or the ideal regressor that has minimum, the least mean square error is the one that predicts the output as the conditional expectation of y given x. Again, this is not available because P is unknown. So we settle for the more modest goal, where when we're only given training samples, try to learn a linear regressor. So we try to predict the output as W times X, where W is some weight vector. The prediction error can be measured again by a loss function, which is high if our prediction W times Xi, the predicted output, is different from the actual output Y, and which is small if they're close to each other. So typical examples include the square loss that is used in ordinary least squares regression, or the Huber loss that just gives less weight to outliers, or the delta insensitive loss, which is used in support vector regression, or the pinball loss from quantile regression. So in this case, we can also replace the empirical risk minimization problem by a distributionally robust problem. Now we pick an arbitrary type P Wasserstein Ball for the moment. And again, we need to define how to be measured transportation distances on the input-output space. So I'm using the same additively separable norm from before, where kappa represents the relative importance of the outputs. So similarly as before, if there is no label uncertainty, and kappa is infinity, and if P is equal to 1, then our worst case prediction loss, again, turns out to become the regularized empirical loss. So this gives a distributionally robust, distributional interpretation of this regularization term here. And there is another interesting case if we use P equals 2, and again kappa is equal to infinity, and we use the squared error. So this is a robustified least squares problem. Then again, the worst case risk corresponds to a combination of the square root of the empirical loss and the regularization term. So in this case, if we actually use the infinity norm to measure transportation costs on the input space, then this will actually recover the generalized lasso estimation problem, which is studied in statistics. So these were unparametric machine learning methods. We can also apply these techniques to parametric models. So imagine that we would like to estimate the mean vector and the covariance matrix of a high m-dimensional normal random vector. For the sake of argument, let's assume that this covariance matrix, the true one, is invertible. Okay? Now, I'd like to argue that in most problems where you're interested in estimating the covariance matrix, you should actually be more interested in estimating the inverse covariance matrix, which is the precision matrix. Turns out that in many problems in economics, engineering, science, the covariance matrix appears in the input of the problem, and the precision matrix, the inverse, appears in the output. For example, in linear discriminant analysis, you use the covariance matrix of the features as an input, and the maximum likelihood estimator that comes out of it depends actually on the precision matrix. In Markowitz portfolio analysis, on the other hand, you use the covariance matrix of the asset returns as an input, but the optimal portfolio weights actually depend on the inverse covariance matrix. Also, in the optimal fingerprint method of climate change detection, this one takes the covariance matrix of the internal climate variability as an input and outputs a climate change signal that depends on the precision matrix. So we should be interested in estimating the precision matrix as much as we should be interested in estimating the covariance matrix. Now, the simplest estimators for mu and sigma are the sample mean and the sample covariance matrix, which just are the actual mean and covariance matrix with respect to the empirical distribution. But of course, this doesn't work very well in the case of high-dimensional data, when the dimension of psi exceeds the number of training samples. As the sample covariance matrix is just a sum of n rank 1 matrices, it cannot be invertible in the case when m exceeds n. So that means in this situation, in a situation of high-dimensional data, we would not have a precision matrix estimator. So instead, we could try to solve a maximum likelihood estimation problem over all candidate mean vectors mu and candidate precision matrices x. So it is well known that because our distribution is normal, that maximizing the log likelihood of the training samples is equivalent to solving this convex minimization problem, which minimizes the negative log det of the precision matrix, and another term which can loosely be interpreted as the inner product of x with the sample covariance matrix. Good news is that this problem can be solved analytically. And the bad news is that the problem is actually unbounded in the high-dimensional setting when m exceeds n. And in the low-dimensional setting, when m is smaller or equal to n, then the optimal solution of this problem is just, again, the sample mean and the sample, or the inverse of the sample covariance matrix for the precision matrix. So we haven't gained anything. So that prompts us to actually robustify this maximum likelihood estimation problem in the following way. So we basically replace the second term in the objective function by a worst-case expectation over all distributions in a type 2 Wasserstein Ball, which is centered at a normal nominal distribution. So that's a normal distribution whose mean vector is the sample mean and whose covariance matrix is the sample covariance matrix. This seems to be a reasonable thing to do, because if you set the radius of the Wasserstein Ball to 0, then this model just collapses back to the normal maximum likelihood estimation problem. So this can be seen as a robustified maximum likelihood estimation problem, indeed. So we hope that we can regularize the problem through the robustification. So luckily, this problem has a lot of structure. It turns out we can use our techniques from the analysis of the Gelbrich risk to reformulate this problem exactly as a semi-definite program. So the Gelbrich bound is exact in that example, right? And we get an STP reformulation. Unfortunately, the STP grows very quickly with the dimension m of the data, and general purpose solvers could only solve small instances. But luckily, this problem has really a lot of structure, and it turns out that we can actually solve it in quasi-closed form. So what we can do is the following. We can prove that the optimal solution for the mean is actually just a sample mean, and that the optimal precision matrix estimator, x star, can be represented, or actually has the same eigenvalues as the sample covariance matrix sigma hat. But it has different eigenvalues. The eigenvalues of our optimal estimator are obtained by perturbing the eigenvalues of the sample covariance matrix by using this formula here. So this formula is an analytical formula, but it involves one unknown parameter, gamma star. And this is the unique positive solution of the algebraic equation at the bottom of this slide. So this is a scalar parameter. So a few observations are in order here. So because the estimator X star and our sample covariance matrix, they have the same eigenvectors, this means that these two matrices, they commute. And this implies that our estimator is actually rotation equivariant. So this means that the estimator applied to the rotated data is the same as the rotated estimator applied to the original data. Rotation equivariance is an important property, according to Charles Stein, of an estimator if we do not have any structural information. And this comes out naturally here in this theorem. We can also prove that all these eigenvectors of our estimator, the X star i's, are positive. So that means our estimator is always invertible, even in the high-dimensional regime where n is bigger than the sample size. And the estimator X star is actually extremely easy to compute. The only thing we have to do is we have to compute the spectral decomposition of our sample covariance matrix. And then we have to solve this algebraic equation, which is a scalar equation. So this can be done by bisection very efficiently. So because the estimator is obtained by perturbing the sample eigenvalues, we refer to this estimator as the this estimator can be interpreted as a nonlinear shrinkage estimator, and that's why we call it the Wasserstein shrinkage estimator. So it turns out that this estimator has many good properties. It exists even if n is bigger than n, as long as our radius of the Wasserstein ball is strictly positive. So it's always available. It always gives us a precision matrix and a covariance matrix. It is rotation equivariant. One can also prove that it preserves the order of the sample eigenvalues. That's another good property, according to Charles Stein, that any decent estimator should satisfy. We can also prove that the condition number of this estimator improves as the level of robustness increases. So if the radius of the Wasserstein ball grows to infinity, the condition number of the X star will converge to 1. The complexity of computing the estimator is very low. It's the same as computing the spectral decomposition of the sample covariance matrix. And we can also come up with out-of-sample guarantees on Stein's loss. That's a loss function for precision matrices. So all of these nice properties were not imposed up front. We didn't dictate them, but they just emerged naturally from our robustified, distributionally robust maximum likelihood estimation problem. So I don't show any numerical results, but we've seen in our paper that the estimator actually performs very well. So it has similar performance as the graphical lasso estimator, but this one can only be computed by solving a high-dimensional semi-definite program. So you need an algorithm. Whereas our estimator is very easy to compute. It's not harder to compute than simple linear shrinkage estimators. So that is a very good properties. Very last example. So we also apply these techniques to minimum mean square error estimation. So this is a problem where you have a signal x, but you don't observe it. You have just a noisy observation, and you would like to infer the signal from this observation. So pretty much like before, we assume that the random vector xi, which consists of both x and y, follows some distribution p, but we do not know this prior distribution, actually. Let's assume, however, for simplicity, that there is a nominal distribution p hat, which is an elliptical distribution, and there is reason to believe that the true distribution is somehow close to that one. So we approach this problem by proposing a distributionally robust minimum mean square error estimation problem. So the estimation problem is shown here. So what we do is we minimize over all estimators of x. So these are just arbitrary measurable functions of the observation y. The objective of this estimation problem is the mean squared error. So that's just the expected value of the squared distance between the true signal and our estimated signal based on the noisy measurement. Of course, we cannot evaluate the true distribution because we don't know it. So we evaluate the worst case expectation over all distributions in a Wasserstein ball around our nominal elliptical distribution. So this estimation problem actually constitutes an infinite dimensional zero-sum game. The statistician optimizes over all measurable estimators, there's measurable functions, and nature optimizes over the infinite dimensional Wasserstein ball. So this seems to be difficult. However, by using the properties of elliptical distributions, one can actually and using a result for Gelbrich bounds, one can prove that this problem is equivalent to a finite convex optimization problem, which optimizes over all covariance matrices sigma xx of x, covariance matrices sigma yy of y, and all cross-covariance matrices sigma xy of x and y. One can prove that this nonlinear STP is actually always solvable, and any optimal solution can be used to construct an estimator psi star that is actually optimal in the zero-sum game in our distributionally robust MMSE estimation problem. So you can see that this estimator is actually linear, so it is an affine decision rule. So what we've done here, we've actually discovered a new class of distributionally robust adaptive distributionally robust problems where affine decision rules are exactly optimal. We can actually also use the solution of this nonlinear STP to construct a least favorable prior. So that is a distribution Q star from within the Wasserstein Ball that forms a Nash equilibrium for our zero-sum game together with the optimal estimator. So it turns out that this least favorable prior is also an elliptical distribution with the same density generator as the nominal distribution, with the same mean as the nominal distribution, but with the covariance matrix sigma star that is taken from the solution of this nonlinear STP. So this nonlinear STP can be linearized by using Schur complement arguments. It can be converted to a standard STP and solved with off-the-shelf software in principle. However, the problem sizes quickly exceed the capabilities of standard software. So it turns out that there is merit actually to solve this nonlinear STP directly by using a Frank-Wolf algorithm. So let me just quickly denote the objective function abstractly of this problem by f and the feasible set by u epsilon. So the Frank-Wolf algorithm starts at an arbitrary iterate sigma k, that's an arbitrary feasible solution. And in step 1, it then solves a direction finding subproblem. So what it does, the algorithm linearizes the objective function around sigma k. So it constructs the first order Taylor expansion, and then just maximizes this linear function over the feasible set to obtain a point dk. Now in the second step, the Frank-Wolf algorithm constructs a new iterate, sigma k plus 1, as a convex combination of the old iterate and the solution of the direction finding subproblem, where alpha k is a judiciously chosen step size. And then in the last step, we just increment k and we go back to step 1. So that's standard Frank-Wolf algorithm. And this algorithm has two key benefits. The first one is that the nonlinear STP we're solving is a very nice one. It has two important properties. The objective function is concave, it is smooth, and the gradient is bounded away from 0. Moreover, the feasible set can be proved to be strongly convex. And for these reasons, one can prove that the Frank-Wolf algorithm offers a linear convergence rate. So it will converge quickly. The more important benefit is the following. It turns out that the direction finding subproblem of this algorithm, so that can be solved in quasi-closed form. So here is the formula for dk. There is one parameter, a scalar gamma star, a bit like before, that we need to determine by solving an algebraic equation. Again, this can be done very quickly by using bisection. So that means that the direction finding subproblem can really be solved extremely fast. So the Frank-Wolf algorithm will converge very, very quickly, much faster than standard software. Okay, so that brings me finally to the end. Some key takeaways about applications of Wasserstein distributionally robust optimization in machine learning could be summarized as follows. So this DRO approach explains many commonly used regularization terms in regression and classification, and thereby gives them probabilistic interpretations. It can also explain why shrinkage estimators are useful, right? They emerge also as solutions of some robustified estimation problems. So the distribution robust approach actually in some cases results in other tractable convex problems that have not a direct interpretation in view of the classical theory of statistics. So it also motivates new regularization schemes. I didn't show that to you, but that's in the papers. And actually the models that we obtain are often equivalent, actually in all the examples we've seen, they're equivalent to efficiently solvable convex programs. Sometimes these convex programs are even solvable in closed form. Maybe there is a need to solve a very simple algebraic equation using bisection. And sometimes they're solvable via very fast first-order Frank-Wolf algorithms. So I think there is I find it very interesting to investigate these problems further, and I think there is a very interesting potential in using this approach for machine learning applications. So that's the end. Thank you very much. Here's some references. The tutorial paper is the one on top. Thank you. Yeah. Any questions? Very late, yeah. So the question is, why don't we use other distance measures for distributions like the KL divergence? The KL divergence has very good justification as well, and this is not, I'm not arguing against KL, but this should rather be seen as a collection of results that show you that there is merit in studying the Wasserstein distance. There is maybe one argument against the KL divergence, and that is what I said about black swans, right? By using the Wasserstein distance, the adversary that plays against us can move probability mass anywhere inside the set Xi. So scenarios that we've not seen in the past can be constructed by the adversary by moving mass anywhere, right? And thereby we implicitly protect ourselves to some extent against these scenarios. Now, under a KL divergence, this would not be possible. Depending on how you use it, either all distributions in the KL ball would be supported on the training samples, or at least the training samples would all have had a positive mass, which seems not so natural. But there's good reason to use KL as well, so I'm not arguing against it. Okay, yeah. Okay. If there are no further questions, then thank you very much for your attention, and have a nice evening.